So now let's say linear triangular element or first order triangular element. This is a linear variation of displacement along the edge of a triangular element. So we will start with the generic form of element stiffness matrix, and we will see the element stiffness matrix for first order triangular element, and we will have some observations. Okay, so this is the element stiffness matrix generic form, and B is a strain displacement relationship matrix, whereas D is a stress strain relationship matrix. So as usual, we will take the simplest case of triangular element. Okay, so we are taking this node 1, 2, 3 are three nodes of triangular element, and node 1 is situated at 0, 0 coordinate. So 2 is on x-axis, and 3 is having a 0, 1 coordinates, and it is on y-axis. And these lengths are 1, and this is also 1, so that we can easily write shape functions. Okay, so this we have seen in last lecture. Okay, how to know the size of k, b and d matrices. So basically degree of freedom per element is okay, here it is number of nodes into degree of freedom per node. So 3 into 2 is equal to 6. So size of matrix is degree of freedom by degree of freedom per element. B matrix size, we know it is 3 is number of stress components. Okay, so sigma ij or epsilon ij by degree of freedom per element. Similarly, D matrix is no, uh, number of stress components by number of stress component. So this is 2D case. So we have only 3 stress and 3 strain components. So this is our displacement function. The first step in FEA is we need to assume this trial function. Okay, using the shape functions, we derive the trial function as discrete quantities. So u1, u2, u3 are x displacement at nodes 1, 2, 3 respectively, whereas v1, v2, and v3 are y displacement at nodes 1, 2, 3 respectively. So we can write a displacement in x and y as a shear function of u n1, n2, n3, and u1, u2, u3. Now we know the shape functions we select such that, okay, for example, if we have to write n1, okay, it should be it should have value 1 at node 1 and should be 0 at nodes 2, 3 or remaining nodes. In that case we can satisfy this, like u at node 1 will be is equal to 1 into u1. That means u at node 1 is equal to u1. So n1, we can say this is a straight line and this will be a n1 function, n2 is x, and n3 is equal to y. Okay? So we satisfy all our conditions. So in matrix form we can write like this, n1, n2, n3, which is n transpose, right? And this is a u vector. Similarly, this y displacement n transpose ve, okay, n transpose, and this is our y displacement vector. And this is a graphical representation of shape functions. Okay. So this is my x-axis and y-axis. So this is the same element, but we are just changing our viewing direction, okay, so that we can draw shape function, which is in this pink color. So this is a perpendicular axis, y and x. Okay. You can imagine that how it looks. Okay. And these are nodes 1, 2, and 3. So n1, as we can see, it is 1 at node 1, and they are 0. It is 0 at nodes 2 and 3. Okay? And it is a linear variation, okay, along the edge of element. Similarly, n2 is 1 at node 2, and it is 0 at other nodes. and n3 is 1 at node 3, and it is 0 at nodes 1 and 2. So now we are done with the shape functions. Now let's see the B matrix for linear triangular element. So we will see this one. So we know for 2D case we have three stress component and three strain components. So this is our strain vector, okay, which is equal to, from our continuum mechanics lecture, we know dou u by dou x. This is dou v by dou y, and this is dou v by dou x plus dou u by dou y. So epsilon 1 1 and epsilon 2 2 are normal strain components. This is our shear strain component. And epsilon 1 1 is equal to dou u by dou x, means x displacement in x direction. This is y displacement in y direction. This is y displacement in x direction plus x displacement in y direction. So from this we can know we need to have the B matrix. So it's a strain and displacement relation. So now this is 2D. So we have u1 v1 both, okay, x and y at node 1, x and y displacement at node 2, x and y displacement at node 3. So for this 2D case and triangular element, this is 6 by 1, this is 3 by 1, and as we know B matrix will be 3 by 6. So how this comes? So we are just deriving dou u by dou x and these terms, okay, on right hand side, and we have just substituted all these values here, and we get this one. So let's see this dou u by dou x. So u, as we know, is okay, this one, okay, and transpose and u e. So since the shape functions are only the functions of x and y, okay, so we need to differentiate only shape functions with respect to x. Okay. So basically dou u by dou x, okay, is equal to dou n1 by dou x u1 plus dou n2 by dou x u2 plus dou n2, sorry, dou n3 by dou x u3. So this is the dou u by dou x, which we are writing in no, complete displacement vector, not only u. Here we have v as well. So this second, fourth, and sixth is a zero. Okay, it will be multiplied with v1, v2, v3, and we get this one. Okay, so this is just a way of presentation. Okay, since we want to have dimensional consistency. Okay, we want to have this side as a 6 by 1, 6 by 1, and 6 by 1, so that we can combine all this. So this is dou u by dou x. Similarly, dou v by dou y. Okay, it is again dou n1 dou by dou n1 by dou y into v1 plus dou n2 by dou y plus v2 plus dou n3 by dou y into v3. And similarly, dou v by dou x plus dou u by dou y, we get something like this. Okay, we can just substitute v and u, okay, from this previous slides, these values, and we get this form for epsilon 1 2. So this once we substitute all these terms here, okay, so this is our displacement vector, and okay, so this is the first row of this one. Okay, so this is the first row, then this one is second row, and this is third row. Okay, so we have to just find dou n1 by dou x. Okay, I'll just show it for few. So we have dou n1 by dou x is equal to, if take differentiate with respect to x, we get -1. Similarly, dou n1 by dou y, we get -1. Similarly, we need to find dou n2 by dou x and dou n2 by dou y, and similarly dou n3 by dou x, dou n3 by dou y. So substituting all those here, the values, we get this matrix. Okay, so this is 3 by 6. Okay, and since this is a strain vector and displacement vector, this becomes our B matrix. Okay. So if I this is a matrix form, I can write simply in uh, linear equations form here. Okay, by multiplying this with this, I get epsilon 1 1 is equal to u2 minus u1. Epsilon 2 2 is v3 minus v1. Epsilon 1 2 as u3 minus u1 plus v2 minus v1. Okay, so we can understand graphically as well here. Okay, if I have this triangle. So to find the strain in one direction, that is in x direction. Okay, from this it is this is u2 and this is u1. So epsilon 1 1 is u2 minus u1. Similarly, epsilon 2 2, which is strain in y direction, like this, v3. Okay, so this is displacement in y direction v3, and this is v1. So epsilon 2 2 is v3 minus v1. Similarly, this is a shear strain. Okay, so shear strain for this triangular element, okay, will be something like this. Okay, so this change in angle, which will be u3 minus u1 divided by 1. Okay, because this length is 1. Sorry, this one. Okay, this u3. Okay, this one u3 minus u1, whatever displacement for node 1. Okay. So u3 minus u1 uh, is our dou u by dou y, okay, plus this is dou v by dou x. So from this we can understand this is a change in angle basically. Okay, so this is our shear strain. Now from this we can observe that, okay, the strain components, okay, two normal strain and one shear strain component, okay, they are constant across the element. Okay, because once we get the uh, unknown displacements after solving the FEA equations, we can estimate the strains, right? But if we see here, the strain components are just a function of u1, u2, u3, v1, v2, v3. Okay, they are not function of x, y. That means it is a constant, okay, across the element. Uh, because it looks there is it is not function of x and y here. Okay, and that is the reason this element is also called a constant strain triangle element. Okay, so with this understanding, okay, we have found b. Now we have to see d. Okay, so before seeing d, let's understand from this. Okay, uh, we can have some practical tips on when to use this linear trie elements. Okay, and these are also applicable to linear tet element. So the linear trie elements, as we know, we do not generally prefer in FEA analysis. Okay, so it should not be preferred in region of interest, but still we can use these elements because these elements are very computationally inexpensive. Okay, and when we, I mean, it does computation very fast, your analysis completes very fast. So it is suggested to use these elements wherever possible. For example, use in the situations where the stress gradients are not high. Okay, so we are not interested in capturing stress gradients in those regions, and these elements can also be used as a filler elements or supporting structures. Okay, that means that this is also known the region of not non-interest. Okay, like filler elements or supporting structures. But we have to be careful. Okay, this supporting structure or where we are using the filler elements, linear trie element, Okay, that should not undergo any large displacement. Okay, otherwise it will not capture that large displacement in terms of bending or any other deformation accurately. Okay, and it will ultimately lead to inaccuracy in overall global behavior. Okay, for example, if I have some structure like this, so I'm just giving some situation. uh, let's take this is something like this. Okay, this is one structure and here we have another block. Okay, and we are applying some load here or pressure here. Now we might say that okay, this is the region which I am not interested. Okay, and this region uh, also not of so interest. So I will do a linear tri-element meshing in this region and this region as well. Here you might use hex elements or second order tri-element, but we have to be careful here. Okay, because when we do apply this undergoes a small strain, it may be the case. Okay, this may be a small strain region. Okay, but this is not a small displacement region. Okay, because when we apply load, this undergoes a bending. Okay, and if we use a linear tri-element, the bending main is not captured properly, as we can see here. Okay, it is a constant across element. Okay, so it will ultimately lead to inaccuracies in global model. Okay, so it may happen like at 10 newton it was supposed to make a contact with this body, but because of a linear tri element, okay, it is making contact at 20 newton. Okay, because linear tri elements are stiffer. So this may lead to inaccuracy is what I am trying to point out here. So we should not use it in case of large displacement. Okay, typically in bending. And also, as we said, no, this is a constant across element. So what happens in typical bending behavior? Okay, let's take this is some uh, beam type of structure. Okay, and we are meshing it with a tri element, linear tri element. Okay, so this undergoes bending, something like this. So when we try to capture, okay, the bending stresses, which are normal stresses, okay, we know this is the typical bending behavior or stresses are something like this. So this is a tensile and this is compressive. Okay, but if we use only one element, okay, if we use only one number of element, okay, as we know it is a constant stress or constant strain element. Okay, it will capture something like this, the stress. Okay, so we will not be able to capture properly. So for that we need a further refinement. So if we use two elements, okay, the two element will show behavior something like this. Okay, across this thickness. So here we have constant strain in upper element, and the lower element will have constant stress, which is compressive. So we need to do a lot of refinement in order to capture this gradient or stress gradient, in other words. Okay, something like this. If four elements, then it will be something like this. So as you can see, we have to do a refinement, and it moves towards uh, the expected behavior, okay, which is a smooth. So this is R. If I take XY, okay, these are okay, epsilon 1 1. Okay. Similarly, epsilon 2 2 as well. Okay, we can see it is we cannot capture the gradients with a fewer number of elements. So tri elements are computationally inexpensive, but we need a lot of refinement. Okay, compared to other element types to capture the stress gradients. So therefore, it is not preferred. Okay, and these are some guidelines. And as we said, you can use it in low, no, sorry, small strain problems, but not in case of large displacement. Other, the very good, approach or strategy, okay, in any FE analysis, we can follow this one. Okay, we can use this linear tri elements or tet elements for preliminary analysis. Okay, so once we get the CAD model, we do not have idea of how this the structure is going to behave. So for a quick idea, we can run the analysis with the first order tri or tet element. And it is also helpful because once we get the feel of physical behavior, we can make some necessary corrections in our FEA model. Okay, if you start with the second order tri or hex elements, it may be possible that the analysis might not converge, and the whatever inputs we are representing in our FEA, we may not be able to take corrective actions on that. So for preliminary analysis, I would generally do this way, that start with linear tri and tet element, and then further next set of few analysis, I will change the element type to some different element types. Okay, so with that, we have seen B element. Now let's see the D matrix. Okay, so D matrix, as we know, it has nothing to do with element type. Okay, it is just whether it's a 2D or 3D case. So in 2D also we have plane strain and plane stress. So we'll take plane strain case. Okay, so we have two normal stress and one shear stress component. Okay, and this is our D matrix. So B and D, we have written B and D. Now this is a K matrix. This is 3 by 3, 3 by 3. B transpose is 6 by 3. So our K matrix is 6 by 6. And what are the limits? Okay, so this is a dV. So for 2D elements, we know dV is thickness, okay, in dx dy. So, and it is a integration of over volume of element. Since T is a element section property and is not physically modeled, okay, we need to take only integration over x and y, that is in plane dimensions. Okay, so here this is the bounding region. Okay, and for that our limit will be y is equal to 0 to 1 minus x and x equal to 0 to 1. So this is this line. Okay, this bounding region, okay, bounding area is x equal to 0, and this is x equal to 1, and y limit is y equal to 0. Okay, and this line. Okay, so we get bounded region. So y is equal to, this line is from this. Okay, we can say it is y equal to 1 minus x. So these are our limits of x and y for a integration. So this from generic form we have written no, element stiffness matrix for linear tri-element. Now we will substitute our B transpose D and B from previous slides into this uh, K matrix. Okay, and we get this one. So this is our B transpose. This term is D. Okay, and this is B, and dx dy, and t we can take it outside, and these are our x and y limits. So we are not going to no do multiplication and take the integration. Okay, we can leave that computation for your exercise. However, it is not important. The main important which I wanted to highlight is a double integral. Okay, so this matrix multiplication, there are three matrices here. Okay, and if we multiply those three matrices, we get 6 by 6 matrix. And outside matrix we have double integral. Now the double integration of the matrix is the double integration of each term in the matrix. Okay, so this integration t will remain outside, this double integral will go into each component of matrix. Okay, so we have double integral of first components. Similarly we have 36 components, so there will be 36 double integrals. This is only for one element. Though we know the element stiffness matrix is symmetric, but still we have to compute at least 18 double integrals. So just remember this key takeaway. Okay. So we wanted to highlight this, no, in order to get stiffness matrix, okay, we need to have double integration. We need to perform double integration for each term in stiffness matrix. Okay, and we will recall this concept in our next or upcoming lecture for Jacobian and other advanced concept. So there, this concept is going to help you.